Wavelet transforms and its applications. Before discussing about wavelets, we have to brief out other other transforms like Fourier series Fourier transform and short time Fourier transform to have an idea about the drawbacks and disadvantages, some limitations of these other transforms. After that, we will move to the wavelet transforms. What are the outcomes we are expecting after completion of this? Who are learning this, they have to understand the wavelets and wavelet expansion systems, find the wavelet transforms in continuous as well as a discrete domain. What is the definition or meaning of a Fourier series? In mathematics, Fourier series is a periodic function composed of harmonically related sinusoids combined by a weighted summation. With appropriate weights or approximate weights, one cycle of summation can be made to approximate an arbitrary function in that interval. As such, the summation is a synthesis of another function. This is the expression we are going to utilize to represent the Fourier series. So, sin t, sin 2t, sin nt all are nothing but harmonically related sinusoid functions with c1, c2, cn are the weighted summations. One of the example is shown here. This red in color wave will give you a combination of multiple frequencies. Then by applying Fourier series, we are able to separate the individual frequency component. This is done by using either Fourier series or some other expressions. Then once you transform these signals into frequency axis, each signal having its magnitude shown here. Then if this is the Fourier transform expansion, how you are going to find out the coefficients c1, c2 or up to so on cn values? Those are nothing but cr equal to integral of 0 to 2 pi f of t sin rt dt by 0 to 2 pi sin square rt dt. By solving this integral part, we will get these coefficients or constants to be 4 by pi r if r is odd, 0 if r is even. Then these coefficients are substituted in this regular expression in place of c1, c2, cn. Then where r is an odd function, c1, c3, c5 are going to be existing. 4 by pi is the common among all for the coefficients, so we are taking out to be 4 by 5. Sin t 1 by 3 sin 3t, 1 by 5 sin 5t up to so on. This is the expansion for the square wave function shown here. If you are considering this is f of t, may be the expected function or synthesis function. Then if you are considering only single sinusoidal function, the error is going to be more. If you are considering two functions, error is going to be somewhat reduced as compared to single one. Then look at here, this is the expected square wave. For this, we are going to approximate the function. Then if you consider only single sinusoid, error going to be more. Here error going to be more. Then 4 by pi sin t plus 1 by 3 sin 3t, error is going to be somewhat reduced. Here we consider two sinusoidal functions. Then we are going to consider three sinusoidal functions, error is going to be somewhat reduced as number of coefficients goes on increasing. Then the original function and the synthesis function having somewhat closer approximation. Like this, to get this type of sharp variations, we should have infinite number of sinusoid functions. So sudden variations or sharp variations can be observed by using Fourier series, means it requires infinite number of functions. This is the problem with the Fourier series representation. And one more problem here is nothing but this is a synthesis, this is the original function. For this, by using sinusoid functions, approximation going to be taken like this. And In this case, we have an idea about from this synthesis function we have these frequency components, but we can't guess at what time these frequency components are going to be generated. We can guess only the magnitudes of these corresponding frequency signals. That means time localization is not possible in a Fourier series. We are able to extract the hidden components of a frequency components of any signal, or once you synthesized that, by increasing the number of frequency components, we are able to generate a synthesized one to be approximate to the original function, but we can't guess at what time the frequency component is going to be generated. This is the problem with the Fourier series representation. Even though the Fourier series is used to transform time domain to frequency domain, we are able to get the frequency components only. We are not able to recognize at what time which frequency was generated. That means time details of the given signal in the frequency domain not possible. That means time localization of frequency components not possible. With this we will wind up, then we will observe the second part.